Hi, this is Gangadhar, lecturer in mathematics from Giraj Government College, Nizamabad. So today's topic is in mathematics BSC second year in the real analysis. So monotone sequence and Cauchy sequence. So first definition of sequence. So what is a sequence? Sequence is a function from natural numbers to real numbers is called a sequence. So sequence is a function from natural numbers to real numbers is called a sequence. So in the sequence, so constant sequence Sn equal to k value is any real number, then that sequence is called a constant sequence. So now monotone sequence. So in the monotone sequence, first we learn increasing and decreasing sequences. So increasing sequence. So increasing sequence means in a sequence all terms are increased. All terms are increased. Then that sequence is called increasing sequence. So in the sequence all terms are decreasing. Then that sequence is called decreasing sequence. So a sequence Sn is a sequence of real numbers and it is called increasing if Sn less than or equal to Sn plus 1 for all n, and a sequence is called decreasing sequence if Sn greater than or equal to Sn plus 1 for all n belongs to n. So in the sequence terms, S1 less than or equal to S2 less than or equal to S3 less than or equal to so on, Sn less than or equal to Sn plus 1, then that sequence is called increasing sequence. And in the sequence S1 greater than or equal to S2 greater than or equal to S3, so on, Sn greater than or equal to Sn plus 1, then that sequence is called decreasing sequence. So it is the definition of increasing and decreasing sequence. Suppose Sn equal to n square. Sn equal to n square, the sequence terms are 1, 2, 1, 4, 2 square, 3 square, so on. So the values are increasing. So we say that it is increasing sequence. Suppose Sn equal to 1 by n. So the sequence terms are 1, 1 by 2, 1 by 3, 1 by 4, so on. So here the terms are decreasing. So we say that it is decreasing sequence. So now the definition of monotone sequence. So monotone sequence is a sequence is either increasing or decreasing, then it is called a monotone sequence or monotonic sequence. Monotone sequence or monotonic sequence means a sequence is either increasing or decreasing. So either increasing or decreasing, then it is called a monotone sequence. So some examples. So first an equal to n cube. An equal to n cube. So terms of sequence an are 1 cube, 2 cube, 3 cube, 4 cube, so on. Means so 1, 8, 9, 27, 64. So this way we define infinite terms. So here the terms are increasing. So terms are increasing means this sequence is increasing sequence. This sequence is increasing sequence. So next example, bn equal to 1 by n square. Bn equal to 1 by n square. So the terms are sequence terms are 1, 1 by 4, 1 by 9, 1 by 16, so on. So the terms values are decreasing here. The terms values are decreasing here. So we say that it is decreasing sequence. So now one sequence Cn equal to 2. 2 is constant. So here the terms of sequence are 2 comma 2 comma 2 comma 2. So all values are constant. So it is constant. So this sequence is called either increasing or decreasing. So this sequence is called either increasing or decreasing. So one more example here. So dn equal to minus 1 to the power n. Dn equal to minus 1 to the power n. So here terms of sequence are -1 comma 1 comma -1 comma 1 comma -1 comma 1. So this way we define sequence terms. So here we have in the sequence only two terms, -1 and +1, -1 and +1. So we say that this sequence is neither increasing nor decreasing. This sequence is neither increasing nor decreasing. So this way we define types of sequences: increasing sequence, decreasing sequence. So if the sequence is increasing or decreasing, then we say that it is monotone sequence. So now here we have one theorem. So it is convergence of monotone sequence. So how monotone sequence is convergent means, so a monotone sequence is convergent if and only if it is bounded. So a monotone sequence is convergent if and only if it is bounded. So it is the convergent of the monotone sequence. So now proof of the theorem. So first we will take Sn is monotone convergent sequence and we show that it is bounded. We will take Sn is monotone convergent sequence, then we show that it is bounded. So we know that every convergent sequence is bounded. So we know that every convergent sequence is bounded. So we say that monotonic sequence also, if the monotonic sequence is convergent, then we say that it is bounded. So if monotonic sequence is convergent, then we say that it is bounded. So it is the first part of the theorem. So now in the second part, so reverse case we will take. If sequence Sn is bounded, then we show that a monotone sequence is bounded, then we show that it is convergent. A monotone sequence is bounded, then we show that it is convergent. So it is the reverse case, second part. So in the second part, first we will take sequence Sn is monotonic means it is either increasing or decreasing. Suppose here we will take Sn be a bounded increasing sequence. Bounded increasing sequence means, bounded means sequence has supremum and infimum. So let S denote the set Sn such that n belongs to n, and let U equal to supremum S. So let U equal to supremum S. So since S is bounded. Next, and U is any real number. So we show that limit Sn equal to U. So we show that limit Sn equal to U. Means, so U is limit of sequence Sn, and we say that if limit exists, then we say that sequence is convergent. So let epsilon greater than 0, let epsilon greater than 0, if U is supremum of sequence Sn, then U minus epsilon is not upper bound. So if U is supremum, supremum means least upper bound. So here least upper bound is uniquely exist. So if U is supremum, then U minus epsilon is not upper bound. Not upper bound means, so Sn greater than U minus epsilon. Not upper bound means Sn greater than U minus epsilon. If it is upper bound, then definition Sn less than or equal to U plus epsilon. So if it is upper bound, Sn less than or equal to U. Not upper bound means Sn greater than U minus epsilon. So here there exists n such that Sn greater than U minus epsilon. Next, U is supremum of Sn. Supremum of S. U is supremum of S means, supremum means it is upper bound. Upper bound definition is Sn less than or equal to U. Upper bound definition is Sn less than or equal to U or S less than or equal to U. So that implies we write Sn less than or equal to U means Sn less than U plus epsilon. Sn less than U plus epsilon. So here Sn greater than U minus epsilon and Sn less than U plus epsilon. From these two we write U minus epsilon less than Sn plus 1 for all n belongs to n. So it is the definition of limit of sequence. So that implies we write mod Sn minus U. Mod Sn minus U less than epsilon for all n greater than or equal to n. So mod Sn minus U less than epsilon for all n greater than or equal to n. Therefore we say that U is limit of sequence Sn, and we say that sequence Sn is converge to L. Sequence Sn is converge to U. So therefore, every monotonic sequence is convergent if and only if it is bounded. So now the one problem. So a sequence Sn is defined by S1 equal to 5 and Sn equal to Sn minus 1 square plus 5 by 2 Sn minus 1 for n greater than or equal to 2. So n values are start from 2 to infinity. So then find S2, S3 so on terms of sequence. Second, show that sequence is decreasing and convergent. Third one, also find limit of sequence Sn. So here the sequence definition S1 equal to 5, Sn equal to given. So we find the next terms in the sequence. So next terms are, so in the Sn we substitute n equal to 1. So n equal to 2, S1 square plus 5 by 2 S1. S1 square plus 5 by 2 S1 means S1 square 25 plus 5 30 by 10. 30 by 10 means 3 S2. S3 value we get 7 by 3, we write approximately 2.33 so on. So this way we find terms of sequence. So next we show that sequence is decreasing and bounded. Sequence is decreasing and bounded. Sequence is decreasing and bounded. We show that. So decreasing means Sn greater than Sn plus 1. Decreasing means Sn greater than Sn plus 1. Then we say that sequence is decreasing. So here we see the terms of sequence. So terms of sequence are start from first term S1 equal to 5, so S2 equal to 3, S3 equal to, so on the values are decreasing. We will see in the sequence terms values are decreasing. So we say that it is a decreasing sequence, but how? Means first we will take root 5 less than Sn plus 1 less than Sn less than or equal to 5. So here the first term of sequence Sn equal to 1. So next S2 equal to 3 means, so S1 less than S2, S1 less than S1 less than S2, 5 less than not 5 greater than 3, S1 greater than S2, 5 greater than 3. So S1 greater than S2, 5 greater than 3. Next S2 greater than S3, not first S2 greater than S1. So 5 greater than 3, 5 greater than 3, S1 greater than S2. Next S2 greater than S3. So on this way Sn greater than Sn plus 1. So this way Sn greater than Sn plus 1. So we say that sequence Sn is decreasing. Sn greater than Sn plus 1 means sequence Sn is decreasing. So here in the sequence first term 5, second term 3. So 5 greater than 3, S1 greater than S2. Next 3 greater than some value, S2 greater than S3. So on we will write last term Sn greater than Sn plus 1 means sequence Sn is decreasing. So root 5 is, and the sequence values are Sn greater than root 5. So root 5 is lower bound of sequence, means sequence is bounded below. So therefore sequence Sn is decreasing and bounded below, means it is convergent. So bounded increasing or decreasing means it is monotone sequence, and it is upper bound monotone increasing sequence converges to its supremum. Monotonic decreasing sequence is converges to its infimum, means root 5 lower bound value. So sequence Sn is convergent. So now we find a limit of the sequence, that is limit Sn value. So limit Sn value, suppose limit Sn equal to, we will take S, then limit Sn plus 1 also S. So limit Sn plus 1 also S. So but Sn plus 1 equal to Sn square plus 1 by 2 Sn, Sn square plus 1 by 2 Sn. So here we write Sn plus 1 limit is s, and Sn limit also s plus 1 by 2s. So 2s square equal to s square plus 5. So s square equal to 5, then s equal to root 5. So here s square equal to 5 means s equal to plus or minus 5. But we want least positive, not least positive. We want positive value. We want positive means root 5 is the positive value. So limit of sequence is root 5 here. The next problem. So s1 equal to 1, Sn plus 1 equal to 1 by 3 into Sn plus 1 for n greater than or equal to 1. So find s2, s3, s4. Use induction to show Sn greater than 1 by 2 for all n, and show sequence Sn is decreasing. Next, limit Sn exists, then find limit Sn value. So first terms of sequence are, first term S1 equal to 1, Sn plus 1 is 1 by 3 Sn plus 1. So n value start from 2, greater than or equal to 1 means start from 2. S2, S1 plus 1 equal to S2, 1 by 3 S1 plus 1. So S1 1 plus 1 2 by 3. So S2 is 2 by 3. Next S3 is 5 by 9. So on S4 is 14 by 27. So this way we define terms of sequence. So now we show that Sn greater than 1 by 2, Sn greater than 1 by 2 for all n. So we will use mathematical induction here. So what is mathematical induction means? First we show that given statement is true for n equal to 1. Next we will take it is true for n equal to k. Then we show that given statement is true for n equal to k plus 1. So first we will this assertion we will take from part 1. It can Sn greater than 1 by 2, Sn greater than 1 by 2. So we will take P1 is true means it is statement is true for P1, statement is true for n equal to 1, statement is true for n equal to 1. So what is S1? First n equal to 1 means S1. So S1 term value is 1. So 1 greater than 1 by 2. So 1 greater than 1 by 2 means it is a true statement. It is true statement. Next we will take the statement is true for n equal to k. The statement is true for n equal to k. Then so sk value greater than 1 by 2. Sk value greater than 1 by 2. So here Sn plus 1. Sn plus 1 equal to 1 by 3 into Sn plus 1 given. Sn plus 1 equal to 1 by 3 into Sn plus 1. So here Sn value is greater than 1 by 2. Sn value is greater than 1 by 2. Here we write greater than 1 by 3 into 1 by 2 plus 1. So total value we get 1 by 2. Total value we get 1 by 2. So Sn plus 1 greater than 1 by 2. Sn plus 1 greater than 1 by 2. So Sn greater than 1 by 2, then Sn greater than 1 by 2, Sn greater than 1, if Sn greater than 1 by 2, then Sn plus 1 also greater than 1 by 2. So therefore we say that by mathematical induction, so given statement is true for every value of n, Sn greater than 1 by 2. So for all n. So next we want so note the sequence values lies between 1 by 2 and 1. Sequence values are lies between 1 by 2 and 1 means it is bounded sequence. Sequence is bounded sequence. So it is decreasing and bounded sequence. So we say that it is convergent sequence. So convergent sequence means limit exists. So limit Sn equal to s we will take, then Sn plus 1 limit also s. So here we substitute the values. So Sn plus 1 equal to Sn plus 1 by 3. So we Sn limit is s, Sn limit s and Sn plus 1 limit also s. So 3s equal to s plus 1, that equal to we get s equal to 1 by 2. So 1 by 2 is the limit of the sequence. So here Sn greater than Sn plus 1 terms are increasing, so means it is a decreasing sequence. So next problem. So prove that the sequence Sn equal to, prove that the sequence Sn equal to 3n minus 1 by n plus 2 is increasing and bounded above, increasing and bounded above. So increasing, means definition is Sn greater than or equal to Sn plus 1, Sn less than or equal to Sn less than or equal to Sn plus 1, then sequence Sn is called increasing. Sn less than or equal to Sn plus 1, then sequence Sn is called increasing. So first we write Sn value 3n minus 1 by n plus 2. Next we write Sn plus 1 value. So n plus we write n plus 1, then we get the term is 3n plus 2 by n plus 3. So next we find Sn minus Sn plus 1. Sn minus Sn plus 1 value we find. That value we get minus 7 by n plus 2 into n plus 3. So Sn minus Sn plus 1 value we get minus 7 by n plus 2 into n plus 3. So n belongs to z plus means it is minus 7. So in the numerator minus 7 is there means it is negative. Its value is less than 0. Minus 7 value is negative. So its value is less than 0. So now Sn minus Sn plus 1 less than 0 for all n belongs to z plus means, so that implies we write Sn less than Sn plus 1. Sn less than Sn plus 1 for all n belongs to z plus. So therefore we say that given sequence is increasing sequence. Therefore we say that given sequence is increasing sequence. So here it is sequence, given sequence is increasing. Next we want upper bound of the sequence. We want upper bound of the sequence. So in the Sn we write 3 into n plus 2 minus 7 by n plus 2, that equal to 3 minus 7 by n plus 2. 3 minus 7 by n plus 2. So that value less than 3. That value less than 3. So we say that 3 is upper bound of sequence Sn. 3 is upper bound of sequence Sn. Means it is bounded above. So therefore sequence is increasing and bounded above means it is convergent sequence and sequence is converged to 3. Or here direct we find the limit of Sn. Limit Sn equal to 3n minus 1 by n plus 2. In the numerator and denominator n common, then we get the limit value is 3. Limit value is 3. So we say that it is increasing means bounded above and its limit is 3 convergent to 3. So next problem. So find the prove that the sequence Sn equal to 3n plus 4 by 2n plus 1 is decreasing and bounded below. Decreasing and bounded below. So decreasing and bounded below. Decreasing definition. So decreasing definition is Sn greater than Sn plus 1. So Sn greater than Sn plus 1, then we say that sequence Sn is decreasing. Sn greater than Sn plus 1, then we say that sequence Sn is decreasing. So here we write Sn value 3n plus 4 by 2n plus 1. Also we write Sn plus 1. In n plus we will take n plus 1. Then we get Sn plus 1 term is 3n plus 7 by 2n plus 3. 3n plus 7 by 2n plus 3. So next we find the value Sn minus Sn plus 1. Sn minus Sn plus 1. So that value we get 5 by 2n plus 1 into 2n plus 3. So Sn minus Sn plus 1 value we get 5 by 2n plus 1 into 2n plus 3. So it is positive. If n belongs to Z plus means this value is positive, means it is greater than 0. So the value is positive means it is greater than 0. So now Sn minus Sn plus 1 greater than 0 means Sn greater than Sn plus 1. So Sn greater than Sn plus 1 for all n belongs to Z plus. Then we say that sequence Sn is decreasing. Sequence Sn is decreasing. So next we find a lower bound of the sequence. So direct we find a limit of the sequence. So if limit of the sequence here n common means 3 by 2 is limit of the sequence. We say that 3 by 2 is lower bound. 3 by 2 is because sequence is decreasing means it contains lower bound. So 3 by 2 is lower bound of the sequence. So we say that it is bounded below. So therefore sequence Sn is decreasing and bounded below. So therefore it is convergent and converges to 3 by 2. So next problem. So Sn equal to 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 plus so on plus 1 by n into n plus 1. Show that sequence Sn is convergent. Show that sequence Sn is convergent. First given sequence is Sn. Next we find Sn plus 1. Sn plus 1 means so first term, second term, third term, nth term and n plus 1th term and n plus 1th term. So first, second, third, so on nth term and n plus 1th term is 1 by n plus 1 into n plus 2. So next we find the value Sn plus 1 minus Sn. So we find the value Sn plus 1 minus Sn. That value we get 1 by n plus 1 into n plus 2. So Sn plus 1 minus Sn equal to 1 by n plus 1 into n plus 2. So if n belongs to n, then this is positive value. If n belongs to Z plus, then this is positive value. Means it's this value greater than 0. This value greater than 0. So Sn plus 1 minus Sn greater than 0 means Sn plus 1 greater than Sn. Sn plus 1 greater than Sn, or we write Sn less than Sn plus 1. Sn less than Sn plus 1 means sequence is increasing. Sn less than Sn plus 1 means sequence is increasing. So therefore given sequence is increasing sequence. So next also we write in the sequence Sn equal to terms are 1 by 1 into 2 plus 1 by 2 into 3 plus so on 1 by n into n plus 1. So these terms we write first value 1 by 1 into 2 means 1 by 2. That value we write 1 minus 1 by 2 plus next 1 by 6. 1 by 2 into 3 means 1 by 6. That value we write 1 by 2 minus 1 by 3. 1 by 2 minus 1 by 3. Next value we write 1 by 3 minus 1 by 4. This way nth term we write 1 by n minus 1 by n plus 1. So 1 by n minus 1 by n plus 1. So here, so first 1 minus 1 by 2 plus 1 by 2 cancel. Minus 1 by 3 plus 1 by 3 cancel. So on plus 1 by n minus 1 by n cancel. So we get minus 1 by n plus 1. So here 1 minus 1 minus 1 by n plus 1. 1 minus 1 by n plus 1. If n tends to infinity, then 1 by n plus 1 tends to 0. N tends to infinity, then 1 by n plus 1 tends to 0. Means sequence values are less than 1. So Sn less than 1. Sn less than 1 for all n belongs to Z plus. So Sn less than 1 means 1 is upper bound of sequence. 1 is upper bound of sequence. So therefore it is bounded above. Bounded above. So now sequence is increasing and it is bounded above. So we say that sequence is convergent and converges to 1. So next problem. So Sn equal to 1 by n plus 1 plus 1 by n plus 2 plus 1 plus 1 by n plus 1. Show that this sequence is convergent sequence. Show that this sequence is convergent sequence. So first Sn 1 by n plus 1, 1 by n plus 2, so on 1 by n plus 1. Next we write Sn plus 1. So Sn plus 1 means here n plus we will take n plus 1 means first term, second term, so on nth term and n plus 1th term also, n plus 1th term also. So we find Sn plus 1 minus Sn. Sn plus 1 minus Sn. So this value we get 1 by 2n plus 1 into 2n plus 2. This value we get 1 by 2n plus 1 into 2n plus 2. It is greater than 0. It is greater than 0 for all n belongs to z plus. Means Sn less than Sn plus 1. Sn less than Sn plus 1. So we say that given sequence is increasing sequence. Given sequence is increasing sequence. So next in the mod Sn. In the mod Sn means mod 1 by n plus 1 plus 1 by n plus 2 plus 1 plus 1 by n plus n. So here 1 by n plus 1 value less than 1 by n. 1 by n plus 1 value less than 1 by n. 1 by n plus 2 also less than 1 by n. So on 1 by n plus n value also less than 1 by n. So these values we write, these values place we write less than 1 by n. So now less than 1 by n plus 1 by n plus so on plus 1 by n. So here n times sum of 1 by n. N times sum of 1 by n is n by n. That value we get 1. So therefore mod Sn less than 1. Mod Sn less than 1. So mod Sn less than 1 means 1 is upper bound of the sequence. 1 is upper bound of the sequence. Means sequence Sn is bounded above. Sequence Sn is bounded above. So therefore sequence Sn is increasing and bounded above means it is convergent sequence. So now the definition of one more type of sequence. So it is a Cauchy sequence. Cauchy sequence or Cauchy sequence. So now its definition is, so a sequence Sn of real numbers is called a Cauchy sequence if for each epsilon greater than 0, so there exists a number n such that, so n greater than n implies m comma n greater than n implies mod Sn minus Sm less than epsilon, mod Sn minus Sm less than epsilon. So here a sequence Sn of real numbers is called Cauchy sequence if for each epsilon greater than 0 there exists a number capital N such that m comma n greater than n implies mod Sn minus Sm less than epsilon, mod Sn minus Sm less than epsilon. So this n comma m plus we will take p comma q also. So mod sp minus sq less than epsilon for all p comma q greater than n. Mod sp minus sq less than epsilon for all p comma q greater than capital N. So then sequence Sn is called a Cauchy sequence. So it is the definition of Cauchy sequence. So now one example here. So show that 1 by n is a Cauchy sequence. 1 by n is a Cauchy sequence. So Cauchy sequence means mod Sm minus Sn less than epsilon, mod Sm minus Sn less than epsilon, then we say that sequence Sn is Cauchy sequence. So now mod Sm minus Sn, 1 by m minus 1 by n, that equal to LCM m minus n by mn. So 1 by n is common, so 1 by n into 1 minus n by m, so this value is less than 1 by n, so it is less than 1 by n. So for a given epsilon greater than 0, mod 1 by m minus 1 by n less than 1 by n, so that value we will take epsilon, then we say that given sequence is Cauchy sequence. So here 1 by n is positive, so n greater than 1 by epsilon and m greater than n also. So here we get mod sp mod Sm minus Sn less than epsilon for all m comma n greater than n. So therefore we say that sequence Sn is Cauchy sequence. So in the next problem is n square given. So here first we will take Sm minus Sn mod Sm m square minus Sn n square, that equal to a square minus b square form. Means here we write a plus b into a minus b, a plus b into a minus b, so m plus n into m minus n. So it is greater than m plus n, it is greater than m plus n. Suppose m equal to n, m equal to n, then this value 2n, so it is greater than 2n. But n belongs to z plus means total value greater than 1. M belongs to z plus, n belongs to z plus means, so its value is greater than 1. So m square minus n square value we get a greater than 1, greater than 1. So means suppose epsilon equal to 1. So epsilon equal to 1. So there is no positive integer case such that mod m square minus n square less than epsilon. So here capital N value does not exist. Capital N value does not exist. So therefore we say that sequence n square is not a Cauchy sequence. Sequence n square is not a Cauchy sequence. So now in the Cauchy sequence some theorems are there. So first theorem is every convergent sequence is Cauchy sequence. Every convergent sequence is Cauchy sequence. So now proof of the theorem.
Mommy, bore is now.
So suppose limit Sn equal to S. First we will take every convergent sequence is Cauchy sequence, means sequence Sn is converges to S, sequence Sn is converges to S, means its limit value is S. So limit Sn equal to S, limit Sn equal to S. So here we apply limit definition. So mod Sn minus S less than epsilon plus, we will take epsilon by 2. So mod Sn minus S less than epsilon by 2 for all n greater than n. So let epsilon greater than 0, let epsilon greater than 0, mod Sn minus S less than epsilon by 2, and n equal to m we will take then statement mod Sm minus S less than epsilon by 2. So by the definition of limit, so we write mod Sn minus S less than epsilon by 2 for all n greater than n, and n plus we will take m, then mod Sm minus S less than epsilon by 2 for all m greater than n. So these two are definitions of limit, and we show that sequence Sn is Cauchy sequence. We show that sequence Sn is Cauchy sequence means mod Sn minus Sm value is less than epsilon, mod Sn minus Sm value is less than epsilon, then we say that sequence Sn is Cauchy sequence. So here we find the value mod Sn minus Sm value, mod Sn minus Sm value, that equal to mod Sn minus S plus S minus Sm, mod Sn minus S plus S minus Sm. So here we apply triangular inequality. So triangular inequality is mod a plus b is less than or equal to mod a plus mod b. Mod a plus b is less than or equal to mod a plus mod b. So it is less than or equal to mod Sn minus S plus mod S minus Sm. Mod Sn minus S plus mod S minus Sm. But mod Sn minus S is less than epsilon by 2 and mod Sm minus S also less than epsilon by 2. So epsilon by 2 plus epsilon by 2, that equal to epsilon. So therefore mod Sn minus Sm less than epsilon for all n comma m greater than n. So therefore we say that sequence Sn is Cauchy sequence. Sequence Sn is Cauchy sequence. So now second theorem. Every Cauchy sequence is bounded. Every Cauchy sequence is bounded. So now proof of the theorem. First, sequence Sn is a Cauchy sequence. So sequence Sn is a Cauchy sequence means what is its definition? So mod Sn minus Sm less than epsilon. So mod Sn minus Sm less than epsilon for all m comma n greater than n, then we say that sequence Sn is a Cauchy sequence. So first we will take epsilon equal to 1 greater than 0 and n in n such that m comma n greater than n implies mod Sn minus Sm less than epsilon plus we will take 1. Mod Sn minus Sm less than epsilon plus we will take 1. So now mod Sn minus Sm less than 1 for all m comma n greater than n. So here m plus we will take n plus 1. M plus we will take n plus 1. So then mod Sn, then mod Sn is less than 1 plus mod Sn plus 1. So we get mod Sn minus Sn plus 1 less than 1 for n greater than n. Then we write mod Sn less than 1 plus mod Sn plus 1. Mod Sn less than 1 plus mod Sn plus 1. So now capital M equal to we will take maximum of capital M equal to we will take maximum of mod S1, mod S2, so on mod Sn, and in the last term is 1 plus mod Sn plus 1. So in the sequence 1 plus mod Sn plus 1. So mod S1 capital M equal to we will take maximum of mod S1 comma mod S2 so on mod Sn, and last term mod 1 plus mod Sn plus 1. So therefore we say that mod Sn is less than or equal to capital M. Mod Sn is less than or equal to capital M means it is the definition of bounded. It is the definition of bounded. So therefore we say that sequence Sn is bounded sequence. So every Cauchy sequence is bounded. So now next one theorem. A sequence is a convergent sequence if and only if it is a Cauchy sequence. A sequence is a convergent sequence if and only if it is a Cauchy sequence. So now convergent sequence is Cauchy sequence and Cauchy sequence is convergent sequence. So first case is we show that convergent sequence is Cauchy sequence. Convergent sequence is Cauchy sequence. So now convergent sequence. Convergent sequence means first we will take, so sequence Sn is converges to S. Sequence Sn is converges to S. So we write limit Sn equal to S. Limit Sn equal to S, and we apply limit definition. We apply limit definition. So mod Sn minus S less than epsilon by 2 for all n greater than n. So n plus we write m. So mod Sm minus S less than epsilon by 2. Second case. So here we get mod Sn minus S less than epsilon by 2. Mod Sm minus S less than epsilon by 2. So here we show that sequence Sn is Cauchy sequence means mod Sn minus Sm less than epsilon, then we say that sequence Sn is Cauchy sequence. So now mod Sn minus Sm is, we know that mod Sn minus Sm equal to mod Sn minus S plus S minus Sm. So here apply triangular inequality. Mod A plus B is less than or equal to mod A plus mod B. Means it is less than or equal to mod Sn minus S plus mod S minus Sm. So but mod Sn minus S is less than epsilon by 2 and mod Sm minus S also less than epsilon by 2. So now epsilon by 2 plus epsilon by 2 equal to epsilon. So therefore mod Sn minus Sm less than epsilon. So for all n greater than or equal to capital N. So therefore we say that sequence Sn is Cauchy sequence. So here every convergence, therefore we say that every convergence sequence is Cauchy sequence. So it is the first part of the theorem. So in the reverse case we show that if the sequence is Cauchy sequence, then we show that it is convergent. So first sequence Sn is a Cauchy sequence. So what is Cauchy sequence definition? Let epsilon greater than 0, there exists capital N such that mod Sn minus Sm less than epsilon for all m comma n greater than n. So let epsilon greater than 0, there exists capital N such that so mod Sn minus Sm less than epsilon for all m comma n greater than n. So it is the definition of Cauchy sequence. So now we show that sequence Sn is convergent. Sequence Sn is convergent. So now in particular Sn less than, so we write from this statement, we write mod Sn minus Sm less than epsilon means if mod is cancelled, then that value lies between minus epsilon less than Sn minus Sm less than epsilon. Next we add Sm. So Sm minus epsilon less than Sn less than Sm plus epsilon. So here we will take Sn less than Sm plus epsilon for all m comma n greater than n. So this shows Sm plus epsilon is an upper bound of sequence Sn. Sm plus epsilon is upper bound of sequence Sn. So that value we define. So Vn equal to subsupremum of Sn such that n greater than n. So it is less than or equal to Sm plus epsilon for m greater than n. So next Vn minus epsilon. So Vn is supremum, then Vn minus epsilon is a lower bound. Suppose we will take Vn minus epsilon is lower bound of sequence Sm. So here we get Vn minus epsilon less than or equal to infimum of Sm such that m greater than n, say un. So now limit supremum Sn less than or equal to Vn less than or equal to un plus epsilon less than or equal to limit infimum Sn plus epsilon. So that implies, therefore we say that, so for all epsilon greater than 0 we have limit supremum Sn is less than or equal to limit infimum Sn. So from this condition we say that sequence Sn is convergent sequence. From this condition we say that sequence Sn is convergent sequence. So therefore every Cauchy sequence is convergent. So here one problem is there in Cauchy sequence. So the sequence 1 by n is a Cauchy sequence. The sequence 1 by n is a Cauchy sequence. Already we studied. So mod Sn minus Sm value is less than epsilon. So therefore we say that sequence Sn is a Sn equal to 1 by n is a Cauchy sequence. So in the second case, so the sequence 1 plus minus 1 to the power n is not a Cauchy sequence means, so here mod xn minus xm greater than or equal to epsilon. So the values does not exist. So we say that it is not a Cauchy sequence. So here the problem, next problem, the sequence 1 plus 1 by 2 plus 1 plus 1 by n diverges, apply, so that it is diverges by using Cauchy sequence. So first we will take let h equal to hn be the sequence defined by hn equal to 1 plus 1 by 2 plus 1 plus 1 by n. So which was considered if m greater than n, if m greater than n, then we write the value hm minus hm minus hn value. So that value we get 1 by n plus 1 plus 1 by n plus 2 so on plus 1 by m. So now here, since each of these m minus terms exceeds 1 by m, then hm minus hn is greater than, so m minus n by m. So hm minus hn greater than m minus n by m, that equal to 1 minus n by m, that equal to 1 by 1 minus n by m. So in the particular, if m value is 2n, then h2n minus hn is, we get greater than 1 by 2. So m equal to 2n, then we have h2n minus hn, that value we get 1 by 2, greater than 1 by 2. So this shows it is not Cauchy sequence. So this shows we want mod Sn minus Sm less than epsilon value we want, not greater than value. So but here we get greater than 1 by 2. So we say that H is not a Cauchy sequence. So therefore we say that given a sequence is not Cauchy sequence, means it is not a convergent sequence. So thank you.